Hi, my name is Roger Garcia. I'm the operations director for Aquarius Reef Base, and today what I'm gonna do is just cover physics. We're not gonna go into great detail, but just a little overview and just kind of go over some high points or important points. Okay. So real quick, just so we can kind of discuss what we're gonna kind of go over today. We're gonna talk about just the units of measure, but we're gonna be talking about atmospheric pressure. Not going a lot into detail with that, but just a little bit about that. Hydrostatic pressure, absolute pressure, and gauge pressure. And then we're going to go over the gas laws. Primarily, um, I'll go over the definition and stuff like that, but I also want to kind of get into maybe where they would apply, and then not necessarily go over the formula because you guys have the formula obviously, but maybe more to when it would be applicable if you're actually doing some diving operations and you're trying to plan for something. Okay. All right. So real quick, as far as the lengths or distances, you could use meters a foot. I prefer feet, but you can use meters a foot. Um, Sometimes in some of these formulas, you might have to find out what the cubic footage of an object is. As an example, you might have to plan to lift a heavy object from the bottom, and you're going to have to find out what the cubic footage is uh, and figure out maybe the volume of that object and what its weight in water is and all that stuff. So you might have to use cubic footage in some formulas. Definitely pounds, kilograms. Again, I'll probably just stick to pounds, but you can do it however you want. Fahrenheit and Celsius if you're gonna try to do a formula where temperature is one of the variables or factors. The one thing that I will say about a lot of these formulas, especially like temperature, is that you do have to make them absolute. With these diving formulas, if you don't make them absolute, your formula is not going to come out right. And we'll talk a little bit more about that. And well, there it is. So absolute would be Rankine and or Kelvin, whichever one you decide to use, but you do have to make it an absolute. So if you're going to use Rankine, which is the U.S. Standard system, that's what I typically use. You got to add 460 to whatever temperature you're trying to use in your formula, whether it's the first one or the second one. Okay, moving on. All right, so real quick, right? All of you should be divers. If not, um, maybe you got to do a little bit more reading, but all of you are divers and you understand that we deal with pressure. Primarily, of course, we worry about um, just atmospheric pressure. We don't worry about barometric pressure. That the temperature and low pressure systems, high pressure systems that come into the area will change the atmospheric pressure. But as a standard, you guys know that we should always be using 14.7 as uh, that number for um, the formulas or any formulas that you might be using. Especially if you're gonna make it an absolute, no matter what your number is, you always have to add 14.7, of course. Okay, if you're gonna make it absolute. Um, Pressure, we could be trying to figure out air pressure or water pressure. Okay. Um, Sometimes even in the water, right, you might have to figure out air pressure because it's an airspace. Okay. A diving bell, or the Aquarius underwater habitat. All right. So we might have to figure out what the air pressure is. And then you might have to use different units, maybe PSI, maybe something else, depth, anything like that. But as divers, we just not only worry about water pressure, we also have to worry about air pressure in many instances, and you'll see. Okay, so real quick, if you look at the graphic, if you take 1 square inch of the atmosphere, that weighs 14.7. We know that, but it actually has to go to the edge of space in order to get the 14.7. So it's got to go. whatever it is now, 62 miles or something like that. So it's got to be pretty high, but it is 1 square inch of the atmosphere, however high, will produce 14.7. You guys, are typically aware of that. Okay, so here with the hydrostatic pressure, um, we know that 33 feet of seawater is equivalent to 14.7 pounds per square inch. Again, a square inch of salt water, 33 feet deep. Okay, we got to make that distinction. If it's fresh water, it's going to be 34 feet. Now, I do want you to see that note, the second bullet down there where it says increase at a rate of 0.445 psi per foot. All right, specifically for salt water. The reason I'm pointing that out because that is a number that you really need to remember because it is an important number in formulas that are very applicable to certain things in diving, especially in planning when you're talking about differential pressures, a regulator that you need to have an over bottom pressure, or maybe you're familiar with the term intermediate pressure, but that is important. And what I'm talking about is this right here. Okay, so again, let me try black here. So again, if you look at 0.445, that is how much a square inch of salt water square foot inch, is that right? Square foot inch, yeah. Square inch, 1 foot high, 1 foot deep, weighs 0.445 of a pound. Why is that important? Okay, because that is the figure that you're going to use when you're trying to figure out psi at a certain depth. So if I asked you, okay, what is the pressure at let's say 60 feet? What is the pressure at 60 feet? And again, not absolute pressure, but just what is the pressure at 60 feet in psi? Okay, now you would say you have to take your depth, and we said 60. Okay, 60 feet times 0.445. Go ahead and figure that out real quick. And I'm going to do it with you. So we have 60 times 0.445. All right, and that's basically 26, not feet, right? But 26 psi. So 26.7 psi. If you want, you can round that up just for, just being safe, depending on what you're using that formula for. So it's 27 psi. 27 psi at 60 feet. Okay, so why is that important? All right, so let's take the regulator analogy that I was using. Okay, if you take your scuba regulator with you in your tank, right, and you guys are familiar with that, you have your first stage regulator that reduces the high pressure to a workable pressure or breathing pressure that works against the surrounding water pressure so you can breathe easy. All right, imagine if I set that first stage regulator to 27 psi and you go to 60 feet. Okay, you're going to be able to breathe, but you're going to be working really hard. You're going to be breathing hard to suck that out and work and try to get your lungs to expand against that water pressure. Okay, so what you would do then is say, okay, well, I need a certain amount of pressure above that, so it's easier for me to breathe and expand my chest against that ambient water pressure pushing back against the lungs. Okay, so let's, typical scuba regulators are, manufacturers setting anywhere from 135 psi to 145 psi. So keeping it simple, let's say that I set the regulator to 130 psi. All right. Now it senses that the first stage regulator on your scuba equipment that senses that water pressure, the ambient pressure, and it adjusts for that. So it matches it, and then we're adjusting it to give you another 130 psi. All right. So obviously that's let me erase this. That's 157 psi that is helping you push against the water pressure. That way, there's less respiratory effort. You don't have to work so hard. The muscles don't have to work so hard. You don't get as tired. Okay, so what does that really mean in the end? Yeah, okay, that's great. But what that does too, from the medical perspective, is you're not producing as much carbon dioxide within your body because you don't have to work so hard. Okay, you're not really having this big respiratory effort. Okay, so that's why that 0.445 is really important. Sometimes if you're trying to plan things, related to breathing under pressure. Okay. All right. So if you're gonna do absolute pressure, again, you guys are probably familiar with it. All you got to do is add 14.7. So if you're ever taking a test or these quizzes, be sure that you read what they're asking for. Are they asking for PSI or PSIA? All right. All right. So real quick, gauge pressure. All right. Gauge pressure is the pressure being read. It doesn't matter what that gauge is reading, but if it's gauge pressure, depending on where it is, you guys are more familiar with the typical um, high pressure gauge that you read on your scuba cylinder. So let's go with that, right? When you're reading that, it's only the pressure that's being measured, not taking into account atmospheric pressure. Okay, so when it's reading 0, that your cylinder still has 14.7 because it's the atmospheric pressure in there, it already has it, but it's not taking that into account. Okay, so it's not 3,000 for 3,014, right? It's just 3,000 because it's not taking that into account. All right, so let's talk a little bit about the gas laws. So we have factors that we have to take into account when we're going to do the formula. So when you read a question on one of the quizzes, or maybe when you get asked something, there are factors that we have to take into account when we're doing these formulas with these gas laws, and those are the factors of pressure, volume, and temperature. Okay, and sometimes the question will say at a constant temperature or at a constant pressure. So you have to kind of keep that in mind. Some of it is going to be a constant because you have the general gas law. Because basically, of those factors, usually if there's a change in one, there's a corresponding change with one or both of the other ones. Okay, so sometimes these questions on the quizzes and tests will tell you that at a constant temperature and so on. Okay, so be watching out for that. All right, so Boyle's law. Boyle's law basically is that formula that you see up there, the P1, V1 equals P2, V2, depending on what you're asking for. Are you trying to solve for volume 2 or pressure 2? All right, but one of the things that I always try to tell students about Boyle's law, which you guys probably already read the law itself, but basically this is the law that applies in diving to barotrauma or squeezes. Okay, if pressure increases, volume decreases. If pressure decreases, volume increases. All right, where does that apply? Your ears. Your ear is an airspace, and if you're coming up and you trapped compressed gas in your ear because you can't squeeze because you can't clear. Okay, so real quick again, um, this, when you apply it to diving, this is the law that basically relates to squeezes. Right. So, as pressure increases, volume decreases. As pressure decreases, volume increases, right? Especially when it's an expandable container. Like let's take your middle ear. Middle ear space is an airspace. If you can't clear, okay, you can't do a Valsalva, and that gas is trapped in there, it's either going to compress or expand because the eardrum, and there's a couple of other membranes in the middle ear. You have the oval window and round window. Those membranes will either bulge inward with a negative pressure, or they'll bulge outward with a positive pressure within that middle ear space. But here's the thing, right? Eventually, your eardrum or those other membranes will rupture because they can only stretch so much. Okay. So again, Boyle's law applies to squeezes because of that pressure and volume change, and it can cause, an injury or damage to your eardrum. Um, and also, that pressure differential can transfer into your inner ear space, and you got even bigger problems. Pretty much some of that is what we discussed. You guys have it on your slide. As divers, let me make this point. As divers, if you look at our first 33 feet, okay, right up here, 10 meters, that's where we have our greatest volume change. If you guys, remember back to when you got certified or wherever you're at now, right? That's where we have our greatest volume change. So that's where people typically embolize because you have a 50% change in volume. Okay, that's a lot considering. Okay, so if I take a deep breath and I have 5 liters of air in my lungs, and I hold my breath and I go to 33 feet, that's going to be reduced by half just in those first 33 feet. After that, it's a little bit different. In the next 33 feet, it's reduced by 34%. So it's not as much. So as we go deeper, the volume changes aren't as great. Okay. But as divers, always remember the most dangerous, let's say, depth change that causes the greatest volume change is from 33 feet to the surface, or from the surface to 33 feet. There's just an idea. You guys have the slide. Here's a little challenge question for you. You guys can work it out. Okay, and again, this is related to Boyle's law, so you have the formula, plug in your numbers. The one thing that I will note is, you got the picture, and they're talking about, the volume of air inside that the bell. That is a container that is not collapsible or expandable. So really, the air is compressing or expanding, depending on the water pressure, but not the container itself. Okay, so something there is going to be constant. Okay. So you have Charles' law and Gay-Lussac's law. These two together is the general gas law. Okay, you can split them up. That's fine. But in the general gas law, that's the one that basically states, when you have a change in one, you'll have a corresponding change in one or both of the other factors. Okay. But when you look at Charles' law, that's basically temperature and volume. Okay. So if the temperature changes, volume and pressure could change depending on what the question is. And when you look at Gay-Lussac's law, also if temperature changes, pressure can change as well. Okay, and you can combine all these. The formula or the question can include temperature, volume, and pressure, which is the general gas law. Okay, Dalton's law. Um, Sometimes for some reason this law gets people confused and stuff, but this is the law of partial pressure, right? In a mixture of gases, each gas exerts a pressure that is the sum of the total pressure being exerted. Okay, that's great and all that. But as divers, what's really important about partial pressures is how it affects the body physiologically. So let me make this point, right? You guys that are nitrox divers or nitrox certified, you know that typically the recreational community uses a maximum allowable partial pressure of 1.4. They can go as low as 1.3 ATAs of O2 or partial pressures of O2 um, as your threshold for not crossing into an area that can put you more at risk to central nervous system oxygen toxicity, right? You guys are aware of that. But that number, you see it all the time, and sometimes you don't even think about it. You're just doing your thing, analyzing your gas, and yeah, 1.4, 1.4. But really, anytime we talk about partial pressure in diving, really the concern is what that number means, what that partial pressure of that particular gas means to the body physiologically. What is the physiological reaction to that partial pressure? Okay, because it doesn't matter what the gas percentage is. It's when we're diving, it's that final partial pressure. What problems am I going to run into because of the partial pressure, even though the oxygen is still 21%? Okay, as an example, and I think you guys probably know what I'm talking about. But that's probably one of the most important points when it comes to Dalton's law and the law of partial pressure. And then Henry's law. Henry's law is the gas of absorption. This one, as divers, this relates and ties into decompression sickness. The amount of gas that will dissolve in a liquid is almost directly proportional to the partial pressure of that gas. Okay, so meaning that when we dive, we know that the partial pressure of every gas increases. Okay, as that happens, the body has to be in balance with what's in the lungs, the pressure of the gas that's in the lungs. So the body's going to obviously take on more O2, take on more nitrogen. If you're doing technical diving and you got a trimix, same thing. Okay, you guys understand that? You're going to take on more gas. What that means, what this law is all about, is decompression sickness. That's what it relates to. A couple of little pictures of what happens as you increase the pressure. You're going to take on more gases. You guys got that slide. Real quick on this slide, this is all related to what tissues you need to take into account. I'm not going to get into the weeds with this on this lecture, but if you look at this graph or picture on the slide, basically you have tissue half times. This goes all the way back to J.S. Haldane, who was commissioned by the British Navy to develop decompression tables. He is known as the father of stage decompression. But real quick, basically, we have tissues that we take into account. It could be a 5-minute tissue, a 10-minute tissue, a 15-minute tissue, and 45, 75. You can take tissues that are up to 800 minutes if you needed to in saturation diving and stuff. But just to keep it simple, basically from down here to the top is a certain tissue. Okay, basically what it says is that in tissue half times is that if it's a 10-minute tissue, in 10 minutes, it's going to be 50% saturated. So, and then after that, every 10 minutes after that, it's going to be 50% saturated of what's left. So typically it's anywhere from 6 tissue half times all the way up to 9, depending on what tissue half times you take into account. And that's how the dive tables got developed. There's different ways of doing it these days, because of computer software and all that kind of stuff. But it does go back all the way to the early '90s with J.S. Haldane. But again, it's basically taking into account how much a certain tissue is going to take on in a certain amount of time, and it's always by half. Okay, if it's a 10-minute tissue, every 10 minutes it's going to be half saturated until it's fully saturated. This table that you have on your slide, it's just a quick little reference of what is PSIG, and PSIA or PSI. So anyway, it's just a quick little reference for different things that we kind of already talked about. Like, it'll tell you, if you need to divide by 0.445 or you need to multiply by 0.445, which what was 0.445? Think about it. Okay, real quick, the T formula. The T formula is awesome. All right, so and you may already know about it. Let me go ahead and erase this real quick. Okay, so the T formula is very helpful because it can kind of help you do the more common formulas in diving really quick without necessarily having to look things up sometimes. Okay, so if you remember the T formula, you can do quite a bit of math when you're trying to figure out partial pressures of gases, depths in PS, in atmospheres absolute, or just regular depth by subtracting, either 14.7 or 33 feet, whatever the case may be. But real quick, when you do the T formula, over here on one side, it's going to be, you're going to plug in atmospheres absolute. Okay, yes, sometimes you have to figure out atmospheres absolute first before you plug it in. What am I talking about? How do you figure out atmospheres absolute? Right? It's depth plus 33 divided by 33 gives you atmospheres absolute. That's the formula I use. There's another formula which is quicker and easier by adding 1 or something like that. But that's the one I always have in my head. Okay, depth plus 33 divided by 33 equals ATA. Once you figure that out, you plug in your ATA here. Over on this side, it's going to be gas percentage, but expressed in a decimal. Okay, and then up top is partial pressure. All right, so as an example, real quick, if you have your ATA already figured out, you're going to plug it in here. And then if you have your gas percentage, which is a known, you're going to plug it in here, but expressed in a decimal. So if it's 21%, it's going to be, you're going to plug in 0.21. So as an example, 0.21. And then let's say our ATA is 3. Again, just an example. You already did the math. It's 3 ATA. So you've plugged in your numbers into your T formula, and what you want to do is find out what the partial pressure of oxygen, in this particular case, it's a 2179 mix, but we're talking about oxygen, and we want to know what the partial pressure of oxygen is at 3 ATAs. Okay, so you're trying to solve for partial pressure, which is up here. In the T formula, you multiply across, and you divide up. Okay, so in this case, 3 times 0.21, get my iPhone. Okay, it's 0.63. So the partial pressure of oxygen the partial pressure of oxygen in this case is 0.63, okay? Well below the 1.4, which is the threshold for central nervous system oxygen toxicity. So we're fine, right? But the, that's why the T formula is really, really good. And if you want to reverse it and you want to figure out ATA, you could, you have to, plug in, certain things. You could just plug it in and divide or multiply. Okay. I think you guys get the picture. But I highly recommend that remember what you got to plug in to the T formula, because this one is really easy to use, easy to remember, and it applies to a lot of things that we do on a regular basis when we're diving. Again, a quick reference table, you have it in your slide for PSI absolute, atmospheres absolute, and so on. So, you have this slide, real, key points and stuff. But remember those little key points that we kind of hit on. Remember that 0.445 to figure out PSI at a certain depth. That is a value and a formula that is used often in planning, especially when you're trying to deal with ensuring that you have enough pressure, going to a regulator so people can breathe easier in different settings in diving. Okay. Um, Obviously, remember, you got to add 14.7. If there's a quiz or a question, or you're talking with somebody and you're talking about absolute, you do the math. Don't forget to add the 14.7. If you're talking about, PSI, if you're talking about atmospheres absolute, remember you got to add one. Little nuances like that. Okay. Weight of salt water, really fresh water if you want, fine, but the weight of fresh water is important. Salt water to remember, which is 64 pounds per cubic foot. Little things like that sometimes are important when you're trying to plan. Remember that pressure can be presented in different ways, depending on what, who you're talking to, what you're trying to figure out for what specific reason, whether you're using millimeters of mercury, or otherwise, right? Millimeters of mercury is 760, right, for 1 atmosphere versus 14.7 psi. Gas laws, remember Boyle's law is kind of the law that applies to squeezes, and the fact that pressure and volume are inversely related. Gay-Lussac's law and Charles' law, as well as the general gas law. Dalton's law is the law of partial pressure, right? In a mixture of gases, each gas exerts a pressure that is the sum of the total pressures being exerted. Quick example, the easiest one, you got 0.79 of nitrogen, 0.21 of oxygen. If you took those numbers and you multiplied it by 14.7, in fact, let's do it real quick. We have 79. We have 79% nitrogen in the atmosphere, obviously, and then we have 0.21. If you went ahead and took 0.79 times 14.7, my iPhone again. I'm not as smart as you guys. Okay, that's 11.61. That's 11.61 psi. Okay. We do the same thing with oxygen, and guess what? That's going to be about 3 something. It's 3.08 psi. Okay, now do this. Take that This is PSI. And add those two together. Guess what you come up with? 14.7 PSI. Okay, so the sum of the two gases, the sum of the two pressures equals the whole 14.7. Okay, and then again, it changes a little bit when you start dealing with when you are using partial pressures rather than PSI, right? Because then we worry about what is the body's physiological reaction to those sums and pressures, or to those pressures in in percentages. Okay. Oh, and of course, don't forget Henry's law. Henry's law again relates to decompression sickness, right? Um, how much inner gas you're taking on during a dive. That's gonna, of course, determine what your table and schedule is. I know you guys typically dive computers, and the computer tells you everything that you got to do, but your computer's taking all that into account, right? How much it's theoretically tracking how much gas you're on gassing at a certain depth with whatever gas you're inputting into your computer. Okay, but it has to do with decompression sickness. You guys have some videos that we have for you that you can watch about physics, the effects of pressure, and the science of water pressure to kind of, complement all this in your slides. All right, not too bad. Again, it wasn't, to go into a lot of detail with this, just kind of general and point out some important points. So I hope this helps, and for you guys that are going to be down here for the experience, looking forward to meeting you. Thank you very much.